This is Rob McLeod from the University of Utah and the Scientific Computing and Imaging Institute. Welcome to this series of videos held and created in the context of a workshop we recently conducted on the use of uncertainty quantification and our software called UncertainSCI. In this first video, Akhil Narayan will explain some of the basic functionality and goals of UncertainSCI and a high-level view of a little bit of the math behind it. Hope you enjoy this.
Okay, so thanks, Rob, for the introduction, and it's nice to virtually meet all of you who are attending this conference. This slide is meant to show you all the contributors we have to this project that Rob has described. So as you can see, we're from a couple of institutions, University of Utah, Northeastern, and we have expertise in engineering, the biomedical engineering part, certainly mathematics, and we have a great developer team that helps us with this. So this workshop is generally about sort of a high-level introduction to uncertainty quantification, UQ, and to the particular software, which is UncertainSCI, that we've been developing here. So, by the way, SCI is the name of the institute, right? Scientific Computing and Imaging Institute. So UncertainSCI, it's a nice play on words. One of the presenters later today, Sumientra, is the artistic credit for that. So if you need fancy names for software, she might be somebody to talk to. This is a similar slide, just this is all of us. And as I think you've gotten emails about earlier this week, we have set up a Discord discussion channel for this, along with a GitHub discussion channel. And so we encourage you, if there are questions, either about functionality or about installation or software issues that you have about it, please do contact us. We're very open to that. Okay, so this workshop has two main pillars that I think Rob already articulated. The first one is going to be more of an overview introduction to uncertainty, uncertainty quantification. And so this will generally talk about what kinds of things uncertainty quantification is about, in particular related to biomedical simulations. We'll talk particularly about two subsets of UQ techniques, parametric uncertainty, and delving down even further, polynomial chaos. And so that will form the first hour or so of this workshop. We'll talk about that. And the rest of the workshop will be focused on how we use, how we model uncertainty and some of the applications that we look at, and how we use this tool UncertainSCI in order to codify and to measure uncertainty. We'll go over a couple of use cases. And in particular, there'll be a fairly in-depth discussion, I think, about the software and its capabilities. So this is an overview of the workshop. This is the same overview that you've all seen on the website, so there's nothing new here. And so I'll take the first hour or so and talk about UQ introductions and polynomial chaos. I'll leave a little break in between, so we don't get completely glossy-eyed. Then I'll hand it over to Jess and Jake, who will talk about the software and about cardiac bioelectric use case. And then Sumientra will round things out with a neuromodulation case. We've scheduled an extra half an hour at the end for breakout sessions. These sessions are the ones where we really hope to galvanize discussion, to get feedback on maybe functionality or usability you'd like to see. Questions people have about how uncertainty is modeled. We certainly don't have all the answers. There are problems that we don't know, we don't have yet concrete solutions for. And I think these breakout sessions could be a great place to have discussions like this. So we'll talk a little bit more about the formalities of that when we get closer there. For the purposes of all of our talks, so all the morning talks that we have, I think I would encourage anybody who has a question to go ahead and raise it. You can raise your hand in the participants window, or you can type something in chat. I'll try to keep an eye on the chat and the participants list, but my co-organizers have promised me that if I miss something, if somebody has a question, they'll raise it to me. So please don't be shy if there's something that's you'd like to know a little bit more about. although some of the in-depth discussions we might save for the breakout sessions. So, okay, so I'll start now with the first part of this, which is sort of the intro to UQ part. So uncertainty quantification is a fairly broad field, so we certainly don't have time to talk about everything, but at a high level, there are two kinds of uncertainty that may be relevant for the discussion today. The first kind are so-called parametric uncertainties. These are the kind of straightforward ones, the ones where you say, well, look, I have an input parameter to a model, so this might be a conductivity in a cardiac bioelectricity simulation, and that conductivity the actual value of it might be unknown. So you say, okay, well, I'm going to make that a parameter, and I'm going to wiggle the parameter around, and I'm going to try to understand how wiggling that parameter around affects a measurement or an output that I care about. So this is the sort of standard forward problem for UQ. You can generalize this idea for other more interesting parameters, like say a location of an organ or its geometry. And these are, I'd say, clean examples of uncertainty quantification. You endow one of these parameters or all of these parameters with a random with a distribution, a measure, a probability distribution, and then you push that measure forward and you try to see what happens at the output. The more difficult set of uncertainties are so-called model uncertainties. Sometimes these are called epistemic uncertainties. So these arise from things that aren't really related to particular parameters. So this might be model misspecification. Maybe the particular evolution law that you use to predict an output is not correct in reality. And so there's simply a discrepancy between a mathematical model that you're trying to solve and what's actually happening in the real world. You might, for computational convenience, make mathematical simplifications to governing equations in order to facilitate or accelerate computation. So this is a model uncertainty. You're essentially changing the governing equation. And then there's, of course, computational discretization error. I know this community has paid a lot of attention to this in recent years. And however confident that we all might be in simulation paradigms, there is the fact that we're discretizing everything, and so there's an error associated with that. So the theme for this workshop really is that parametric uncertainty is the one that's kind of more straightforward, the one that we can actually talk about meaningfully, and that's the one that we're going to focus on in this workshop pretty much entirely. We're going to focus on parametric uncertainty. The model uncertainty question, which is a real pressing one that we all should be worried about, is something that's a bit more difficult to nail down. It's a bit more nebulous and opaque. It really does depend on the particulars of the application of the problem that you're talking about. And in contrast, the parametric uncertainty that we'll discuss today is fairly uniform in its applicability and its analysis in various situations. So this might be, for example, an overview of a schematic of a parametric uncertainty problem. So in this particular image, I assume my mouse is visible. There are uncertain parameters, which I'm going to call capital P throughout this presentation. These might be things like conductivities, anatomy, geometry. There's some kind of solver, a simulation tool, really, not necessarily a solver, but a simulation tool. And out comes something that's observable. So here it might be body surface potentials. It might be a localized body surface potential. And there's an extra input that I've put on here, these so-called design variables. So many times, we're not necessarily interested in pushing uncertainty forward through something. We're interested in some kind of optimization, inverse, or design problem. So in this particular case, I might ask, what kind of ischemic pattern gives rise to a particular measured potential? And that is a design problem. And so I'm really interested in that question, but I have to take account of the fact that I don't know exactly what some of these parameters are in the model. And so when I talk about this output quantity of interest, I have to take into account the uncertainty P. We'll see pretty soon here that the design variables I'm sort of going to throw out the window because we're mostly going to be talking about forward UQ today. That's not to say inverse or inference is not important. It's simply the scope of the presentation of our workshop today is going to be about forward UQ. The main takeaway from all I'm saying here is that really what's happening is that this output quantity of interest Q is a function. It depends on the value of these parameters P. Okay, so in fact, Q is a function of P, and so Q itself is random if P. the parameters are random. Okay, with this general setup, what kinds of questions or problems do people generally do with this? What is the utility of actually making this kind of model? Well, there are three major things that people like to do with uncertainty. One is the simplest, and that's, again, what we'll concentrate on today. That's forward propagation of uncertainty. I have parameters as input, and I push them forward to an output that I care about observing. And what I'm interested in quantifying are statistics, maybe the mean, the variance, things like this. Sensitivity analysis, are some of my parameters unimportant? Can I ignore them? Parameter screening or reduction, I can get rid of the unimportant parameters and simplify my computational model. So those are sort of straightforward things you can do with forward propagation of uncertainty. The second sort of class of problems is an inference problem, where maybe I really want to know what the conductivity is. And so I'd like to use measurements of other quantities in order to infer the value of the conductivity. In order to do this, I do need a forward simulation. So pretty much every inference or inverse problem requires the ability to solve the forward problem as a corollary. So typically the forward problem is one ingredient to this. The final sort of class of things is related to inverse or inference problems as a design and optimization. And we're not really going to talk about this today, but for example, here's a brain example on the slide of design and optimization. So the parameters P are different from the design variables, and we're trying to wiggle the design variables around in order to, for example, maximize robustness. And again, this particular design or optimization does require a forward solver. So in all of these cases, I really do need to formalize the concept of pushing uncertainty forward through a simulation. And that's, again, to beat a dead horse, exactly what we're going to be focusing on this workshop. We're going to be focusing on parametric uncertainty and forward propagation of it. Okay. So there are three things that we need to pin down in order to meaningfully talk about the parametric forward uncertainty propagation problem. And these are listed on the slide. I need to identify parameters. I need to figure out a distribution for these parameters and an output quantity of interest. And these perhaps seem obvious, maybe. However, certainly in our group, we've spent a lot of time talking around, what are the important parameters to consider as random? What kinds of distributions do we care about? What's the actual quantity of interest that I want to measure at the end? These appear to be fairly simple questions, but this is a big modeling conversation that I think we've spent a lot of time having because it's important to formalize the problem. So to be specific about what I mean, identification of parameters is exactly what you think it is. If you have a forward simulation, there are probably many parameters that you could wiggle around, conductivities, shapes, etc. And the question is, which are the ones that you try to consider in order to propagate uncertainty? So if we're talking about scalar values, say of conductivities, this is not difficult. Okay, that I can model that as a random variable. What if we're talking about stochastic fields? So what if the conductivity is spatially varying? Then at least if I'm talking about the forward simulation, the conductivity has a different value, say at every voxel in my forward simulation. That's the naive strategy. There are other strategies in order to make a more meaningful parameterization. We're not going to talk about them today, unfortunately, but you can do it. There's even a more interesting question, which is that, well, what if the shape of, say, the heart is uncertain? How do I parameterize that kind of uncertainty? And I think Jess later today will show you one strategy for actually doing that. So to boil everything down, I'm going to claim anyway that there are many cases when sources of uncertainty can be meaningfully modeled as finite dimensional parameters. Okay, there's a balancing act that we have to do with this. If we choose a small number of parameters, we may underestimate the uncertainty, right? We may fix parameters at nominal values when in fact they are a little bit random in a cohort, for example. And the danger then is that we don't fully capture uncertainty. That's under parameterization. Okay. There's an additional danger that we over-parameterize things. Maybe we consider one parameter, maybe we consider several parameters to be random when in fact in a cohort they're fairly constant. Okay, so what's the harm in doing that? Well, okay, you have the ability with over-parameterization to capture more uncertainty. The problem is that you have to computationally tease that out. And so there's a balancing act in saying, well, I really want to incorporate as much uncertainty as I can, but I can't go overboard for computational reasons. Okay, and this is a persistent challenge in UQ. This is not particular to anything that we're discussing today. But you'll see a few examples, I think, of sort of running up against this dimensionality issue later today. Okay. So once I identify parameters, then I have to put a distribution down on them. And typically this is the hard part, right? So if I tell you that I have a few conductivities, well, I might ask the question, are some of these conductivities independent of each other? Okay, I don't know, what are the nominal ranges? Maybe you need experimental data or cohort data to figure that out. What's the distribution? What's the density? So I'm calling the density W in this case. What is the density on these parameters? Who knows? It typically is something that you can't measure directly. So you have to make a modeling assumption in this case. And so in frankly, most of what we've been doing, we've been assuming independent parameters. And this creates a lot of computational simplification. But I do want to emphasize that, at least in the approach that we're going to talk about today, we don't need to make this independence assumption. This is not required. But it does make things a little bit easier in terms of analysis. Okay, the third thing is definition of a quantity of interest. So this is, I think, not too crazy. So we're simply going to say, well, look, there's a forward simulation that gives me maybe a state variable output of a partial differential equation. We'll call that U. And maybe I'll just take a localized version of it and call that my actual quantity of interest Q. Okay, and Q could be the identity map. So anyway, the real point here is that somehow someone needs to identify what the output quantity of interest is. Okay, so for the particular application that you may be doing, somebody needs to decide that there's something important that I want to measure that's dependent on these random parameters, and that's the analysis that I want to carry out. Okay, so those are the three basic things that we're going to need to identify, and I'm not pointing this out to be vague and philosophical. You'll see in the later presentations by Jess and Jake and Sumientra that they go through this process of identifying what the parameters are, what their distributions are, and they explicitly provide this information to the software. So this is a theme that you'll see throughout this workshop. So what do we do with this model? Well, what we really want to do is, again, we're interested in what we'll call forward UQ analysis, which really means that I want to understand the uncertainty in Q. Okay. The problem with doing that is that in order to sample Q, I have to run a forward simulation. Okay. To mitigate that, one class of approaches is to develop emulators, so computational emulators. So for the rest of this talk, I'll call Q sub n this computational emulator. N here, we'll see, is an indicator of complexity of the emulator. So for now, you can ignore it. But the real point is that Qn is something that I can simulate very easily. And so compiling statistics or sensitivities or whatever will be pretty straightforward once I construct this emulator Qn. And this is the general strategy that we're going to use. There are two classes of these kinds of emulators. For the purposes of this talk, and I think for time, I won't really belabor them, but they're so-called linear and nonlinear methods. And this doesn't refer to fitting data with a linear line. That's not what this is at all. This refers to the fact that the map from collected data to the emulator is a linear map. Okay, so that's more general and a bit abstract. But the main point maybe is that polynomial chaos methods are one kind of linear method. They're also nonlinear depending on how you do the construction. But there are other choices that people use in the literature. Certainly Gaussian processes are very popular. People are starting to use neural nets. We all like machine learning. There are some more classical versions of polynomial chaos that people tend to call stochastic finite element methods. So there are a lot of choices here. We're in UncertainSCI, both today and in the software, we use linear PC emulators. Okay, so we're going to do a linear reconstruction procedure using a polynomial chaos emulator. And this may be something that some people have questions about, why aren't we using Gaussian processes, or why aren't we using neural nets? And during breaks or the breakout sessions or offline or whatever, I'd be happy to talk about sort of some of the pros and cons of using all these different methods. Okay, for forward UQ analysis, what can you do once you have an emulator Qn? Well, you can sample it a bunch of times. And since you can sample it a bunch of times, you can compute statistics. So standard things like quantiles and means and variances, and that's okay. But what you'll see examples of later today, later in the simulation parts of the talk, are that we can also compute what we call partial variances. So these are variances that are due to certain subsets of variables. And so I've articulated here on this slide sort of a distinction between two kinds of variances that I think you'll see. One is called a global variance, the other is called a total variance. And the difference between these is a bit difficult to wrap your head around. So it took us quite a while to sort of formalize this, but the basic idea is that the global variance of a particular subset of variables is the variance due to the interaction of all those variables, whereas the total variance is due to the variance of the interaction of all those variables and the variances of all the subsets, so even the non-interacting terms. Okay, so the total variance encompasses more than the global variance, loosely speaking. Okay. So we're going to talk about these sorts of things, but at the end of the day, what you can do with these partial variances is compute sensitivities. And again, these are importance indicators. These tell you how important certain variables are. And so if you normalize things, you get these measures of importance. And again, I'm giving you the example of sensitivities here because you'll see these again later today throughout later talks that people do. And I think, I'm not doing enough justice to explain properly what these sensitivities mean. But hopefully through some examples later, we'll see them. Okay, so this is sort of a summary of where we are right now. I've tried to convince you that in order to do forward parametric uncertainty, we really need to identify three things. One is a set of parameters, another is a distribution on those parameters, and then somebody has to identify the forward map, the map from parameters to observables. And so if you plug these three things into some sort of black box forward UQ analysis, then presumably you can construct an emulator and then compute whatever it is that you want at the end, statistics or sensitivities or anything like that. Okay, so this is the abstract idea. And we've built this tool, UncertainSCI, to be that black box forward UQ analysis tool. Okay, so you'll see things about this today. These links should be similar to the ones that you've seen already. This is an open source Python software tool. Again, it performs forward UQ analysis and it's polynomial chaos based. And here are some just eye candy plots of some things that you can do with it. So we can do box plots. We can do, these are just ensemble plots. We compute sensitivities. This is a nice visualization, unfortunately of a brain, not of a heart, but of a brain. And I think it's showing the mean current with standard deviations shown as these cylinders, these raised cylinders. So you can sort of visualize not only what the response is, but where there's sensitivity to these parameters. Okay, and so UncertainSCI performs the analysis that enables you to do these kinds of visualizations.
We hope you enjoyed that video, and it's only the first step in a series of documentation videos and materials that we have that explains how our software works and how you might want to use it for your form of simulations. So please check out other videos in the series, visit us on our website, and contact us if you have questions about UncertainSCI and how it could work for you.